All right, the hardest part here to get right is going to be your data section. Your data section. So we need to understand what data is. Data is that which you measured. That's data. If you collected data, the data goes in the data table. So, those of you who did water displacement, what data did you collect? Raise your hand. What data did you collect? Will. Of what?
Your material.
Absolutely incorrect. I'm glad you said that because I wanted to point that out. Josh.
The volume of the displaced water.
Okay, so one of your data points, one of your datum, I think it's singular is datum, is the volume of the displaced water. In other words, the final volume after you place the object in it. That's not the volume of the object, is it? What's the other datum? The mass. Okay, so you determine the mass to how many decimal places? Who remembers? One decimal place for the mass? Three decimal places. Okay, and the volume should have been to how many decimal places? One. Okay, so you now have two data, the mass of the object and the final volume after you've displaced water with the object. What is the last piece of data, the last datum? Raise your hand. Yes, Dayton.
The length of it.
Well, no, that's, I'm talking about water displacement, people. Allie. Oh, let's talk about that. Let's remember that data is that which you collect. It's that which you measure. Density is mass over volume, which is a calculation. That will go in the calculation section. This is not the place for it. There's one final. Let's review. The mass of the object, the final volume of the object after, the final volume of water after you added the object. And Josh?
Volume of water before.
Yeah. Okay, how about the volume of water before you added the object? Okay? Isn't that what you collected? Now, Will, in order to find the volume of the object, what did you have to do with those volumes?
Subtract.
You had to subtract. And subtraction is a calculation. And calculations go where? In the calculation section. So, if you did water displacement, is this not what it should look like? The piece, right? Number one is the smallest, number two, and you can label that if you want. Number one is the smallest piece, number two next, number three next, number four largest. Mass. Now what happens if I put a G in parentheses there?
You don't have to put units over it.
You do not have to say G, 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 G. A lot of you guys did that. You put G in parentheses, or hertz, or centimeters in parentheses, and you put down centimeter, centimeter, centimeter. Okay, the whole reason to do this is so that you don't have to do G, 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 G. Okay? So by putting milliliters there, you don't have to put milliliters down. It's assumed that everything that is within that column is in milliliters. All right. What about you two teams that did, or maybe there was more teams than that did geometry? What data did you collect? Rachel. What? The height, I will agree with. How did you determine the radius? So you didn't measure radius, did you? What did you measure? Aha. Okay, so you measured the height and you measured the diameter. What else did you measure? The mass. Okay, is that it? Is that all you measured? consulting with her partner. Her partner says yes.
Yeah.
Rachel, is that all you measured? Yes. Then you're done with data. What do you put in the data section? The stuff you measured. Now, if you have this preternatural desire, almost a supernatural desire, to take diameter and cut it in half, be free to do that. But where does that go? Calculation section. So, Rachel and Carrie's data table should look something like this. Mass, diameter, and height. Right? Okay, back to you, Will. All right, Will. In order to find the volume of the object, what did you have to do?
We had to subtract the final volume from the beginning volume.
Now, for you, that was like common sense, and that's why you probably even mentioned it. It's the volume of the object. Because it's obvious that you're supposed to subtract. When you're communicating with people all over the world, should you be obvious? Do you want to leave things out there for people to obviously calculate? No. When you do that, when you assume, well, you know what happens when you assume. You do not assume when you're communicating scientifically. You are as detailed as possible because you want to make sure that no one makes any kind of leaps that they're not supposed to. So, oh, yes, I'm sorry. It explodes after a while. So we'll explain that here in a second. Okay, so Will, what should your first calculation table look like?
Let's see.
This is where you actually calculate.
So we're gonna subtract this displaced water with the mass material in there, and then
Okay, so the final volume,
yes,
subtracted.
from the beginning.
I think it's the other way around, right? Subtract the beginning from the final volume to get a positive integer.
Yes.
And that should give you the...
Volume of the.
Does that table pretty much do it? So notice what I did. I said calculation, piece 1, piece 2, piece 3, piece 4, beginning volume, final volume, and then I said final minus beginning to get the volume in milliliters, right? If you can find a better way to do it, be my guest. I'm not married to this way. It just seemed to me to be the easiest. All right, back to Rachel and Carrie, which you weren't the only ones who measured. What? Why are you pointing toward? What? Oh, Dayton. Oh, throw Dayton under the bus. Got it. All right, Dayton. Now, how did you determine volume? Okay, Rachel, back to you. What did you do to determine volume? What did you calculate? Matthew says he can get it before Rachel can come up.
You take the diameter and make it the radius.
How? Because do you want to make the same mistake that Will did and assume that scientists all over the world know how to do this?
You divide it by the diameter.
Okay, so the first calculation is take diameter from your data section and divide it by 2 in order to get
The
radius.
radius.
Okay, so D divided by 2 gives you R. Next.
And take your height and then plug those two numbers into the volume of a cylinder, which is 4 over 3 pi r squared.
I think that's the volume of a sphere. The volume of a cylinder is... That's sphere, isn't it? It's a cylinder. A cylinder is pi r squared times height. I know. Yeah, but I was corrected in 6th period. It's I'm not a geometry teacher. Do I look like a geometry teacher? No, I don't look like a geometry teacher.
Oh, well then.
Pi r squared times height. I was wondering if I got that wrong with a class. It was this class I got that wrong with.
Yeah, well.
Pi r squared times height.
Now I gotta
Okay, so
pi r squared.
what do we do with r? Now that we have r, what do we do?
We put it into the equation.
No, because it's pi r squared times height.
Pi r squared.
So what do we do with r next?
Squared.
Sarah says we square the r. Okay, so that would be the next. Now we have r squared. What do we do next? Then we can put it into the equation. Pi r squared times height. So, diameter, radius is diameter. Did I have to put down diameter? No, because where is diameter? It's in the data section. But I did it just to be clear. Diameter divided by 2, r squared. Yes?
So, when we're doing it the geometric way, do you want it we can put it in terms of pi? Like 3 pi?
No,
Alright,
absolutely not. What is the units of volume?
Okay, and then, how do you want us to write the equation-wise? Like for the one up above that says, beginning volume and then final volume, do you want us to just put
F minus B is fine.
F minus B?
Final minus beginning.
And then put the answer next to it?
Yeah. Okay? What? That's V equals pi r squared times height. And pi r, yes. Okay, I can't hear Sarah because people are talking. Only Sarah has my permission to talk. Go. Yeah, you fill in the numbers. So, yeah, if this is 25.0 and this is 28.0, it's 3.0. Okay? Proper sig digs, folks. Proper sig digs. Any questions at this point? Yes, BB.
Wouldn't that be 3.0?
You're subtracting, you go with the lowest number of decimal places.
But there's oh, okay.
Subtracting or adding, go with the lowest numbers of decimal places.
Okay.
Any other questions? Now, whether you did it with water displacement or you did it with geometry, are you now ready to determine density? Okay, so you find, do you have to put down mass? No. The mass was found in your data. Okay, you could just put down the equation D equals M over V. I went ahead and put down all the information that was already there so that it's crystal clear. Because I hate to assume. Mass, volume, density is mass over volume, grams over milliliters. And what happens if I put units in parentheses? I don't have to put all the units down. Carson, you weren't here yesterday. You need to come in tomorrow morning to redo the lab. This is an easy, normally if it's a really intricate lab, I do not have you redo it. It just doesn't count for you or against you, but this is so easy, and I already have somebody coming in tomorrow, so you can partner up with them. I'll see you at around 7 o'clock. All right? Now, final step is percentage error. How off were you? Remember, it's true minus observed divided by true, and its absolute value of. All right? But wait, Mr. Moreno, we don't know what the true value is. I'm about to tell you. All right. Who had black? Black. All right, what did you think it was?
I don't have my sheet out with me.
Anderson, what did you think it was?
Same situation as Josh.
And why isn't it out? Since we're going over this. All right, Josh, we'll come back to you. Who has dark brown? Too late. Now you have to wait till the end. Who had dark brown? Dark brown. Sarah, what do you think it was?
PVC.
PVC. You were incorrect. It's phenolic. Phenolic. A lot of these were very close together in density, weren't they? So it's kind of hard. Light tan, or the wood-looking one. Maple. You had maple. Maple. And that goes into the category, well, duh. Ours was the only one that floated. There was another one that floated. Who else had maple? You were over there in the corner on the almost. Okay, that was you. White. Who had white?
That was us.
What'd you think it was? You don't know? You didn't calculate or anything? We'll come back to you, Bronson. Who had red translucent or green translucent? What'd you think it was? Polyurethane. And you? And the answer is, she's right. It was acrylic. It's okay. All of those are really close together. You'll find your percentage error is not that bad. Purple or gray? Purple or gray? Purple or gray?
I don't know what color we had, but I think we got an answer, yeah. I think we got gray.
Okay, what'd you think it was? Yes! Another one right on the money. Good job. Metallic silver. Metallic silver. What'd you think it was?
Aluminum.
Yes! Aluminum.
Nice guess there, Will.
Red opaque. It could have been lead. A very shiny lead. Red opaque. In other words, red and you can't see through it. There was a red that you could see through. Yeah, I think that was yours.
That was us.
Okay, what'd you think it was?
I'm gonna guess polypropylene.
And you guessed right. It is polypropylene. Yellow. Was there a yellow? What'd you think it was? Yes. Man, you guys are doing much better than first period. Polyurethane. And no one had orange. Orange was actually styrofoam. Polystyrene. Okay? So now you know the true value, right? So some of you guys are going to have, you're going to be close, really, really close. Some of you will be hopefully within 15% off. Yes? Which one did you have?
I don't know. It was white.
White. Okay.
Is that one?
Yes! Dang, another one. And?
I mean, as much as I don't want to say it, I'm thinking the true value. What was the black one?
You don't even have it.
Oh, I have a guess.
What do you think it is?
Polymide?
Yes! Dang, you guys are really good in this class. I'm impressed. Yeah, that helps, doesn't it? Yes. Metallic was aluminum.
No, like this, so.
Oh, that wasn't metallic. There was a gray one. Gray is PVC. Oh, there you go. Okay. Yes. Okay, so a lot of you guys wanted to put down average. This is a good place for the average. What will the average do? Those of you who were off, guess what the average is going to help you with? Yeah, it helps you reduce the percentage error by helping correct your mistakes. But there's another way of helping you correct your mistakes, and that's by a graph. So, let's figure out how to do a graph. This is graph paper. Really high-tech stuff, right? Oh, why are you people surprised? What?
I think our geometry teacher did this in 8th grade. She just put graph paper up on the board and made us do everything.
It really wasn't a big deal. I copied and pasted from Google. I mean, if you want to be impressed by me, that's fine. I mean, but this is probably not a good reason to be impressed. There's other attributes that I have that are even more impressive than copying and pasting. All right, what's on the y-axis? What should be on the y?
The dependent.
The dependent, which was? What were you changing? Yes? You were changing the size, which is mass, right? And what were you observing to see how it changed? The volume. So what goes on the y? Okay, and what should you always put in parentheses? What goes on the x? All right. So this is our graph. All right, now, gang, a lot of you guys have trouble scaling things, and you want to break the graph. You can't break the graph. I want everything to start at 0. Everything to start at 0. Everything to start at 0. That's always the best way. Okay? Now, once you take statistics, you can find other ways, but you know what? You guys haven't taken statistics. So I want you to start at 0. All right? So this is what you do. Let's use Rachel's data. What's your biggest volume? 13.5. So let's go just 15. I always like to round up to the highest 5 or 0. 15. And let's see how many squares I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You know what? It's probably big enough for me to go ahead and go to 15. So what I would do is 15 divided by the squares, 15. So each one should be 1 milliliter. Okay, for the mass, what's your biggest mass? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's just go to 12. So that one is also by ones, right? So 12 divided by 11, that's close enough to 1, right? So now we know how to scale this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, 13, 14, 15, whatever. Okay, that's what I do. It's that easy. For me, it's that easy. Find the biggest number and divide it by however many squares you want to use. If you want to use 10 squares, it would be 1.5. Okay? I try to make it as simple as possible. And this one will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When I graph it, this is what I get. Wow, that's a little bit more than a coincidence, isn't it? What is that? What does it look like?
Precise.
It doesn't look precise anything, but it kind of looks like a line. If this is a line, then we say it has a linear relationship. And if it has a linear relationship, what do we call it in math? A direct or indirect relationship? A direct relationship. What that means is, as mass goes up, volume goes up by the same amount. Folks, guess what this is? It's density. Okay, so notice it's not a straight line. Do not connect the dots. The dots are only going to tell you what is obvious, and that is you screwed up this lab. What should it be? A straight line. Why isn't it a straight line? Because you screwed up the lab. Why? Because you were using really imprecise instruments, and you guys are human beings. Okay? So, now that we know that it is a direct relationship, how can we adjust, just like the average adjusted your mistakes, how can we adjust for your mistakes? It should be a straight line, but it isn't because you screwed up. BB? Of? It's called the line of best fit. You don't draw a line through all the dots.
I said as many as you can in one straight line.
Excellent. That is correct. So, start in the origin, and I'm using a piece of paper, so you'll have to forgive me. All right. So, you now have a line of best fit. What is that line of best fit doing? It's correcting your mistake. Now, guess what happens if you find the inverse slope of this? Now, in math, if you find a line, what do you know you probably have to do? Find the slope of the line. The slope of the line tells you that relationship. Okay? But in this case, it won't do us any good to find the slope. We want to find the inverse slope. Why? What is the inverse slope? What slope? Rise over, volume over. Is that going to help us? So what do? So step number 1, scale it. Step number 2, line of best fit. Step number 3, inverse slope. Why do we inverse slope? Because we want it to be change in x over change in y, which gives us density. Mass over volume gives us. So, find some point on this line. Now, why should you not use one of the points that are already there? Why? What? Because that's screwed up. This is messed up. This is close to being messed up, but close to being correct. This is messed up. This is messed up. Don't use those points. Besides, haven't you already used those points? Where? In your data, in your calculations. I mean, you've already determined that. What does the line give you? The actual answer. So, what? Fine. What? You can beg all you want, sir. Yes, if it is so messed up that the line of best fit is messed up, then yes, you're not going to get.
If you were precise and you just like slightly all the points were on one side and you drew the line through all of them and
What is it with your family? Is your little brother the same way? Your big brother would argue with God if he could. Wait a minute, you don't understand. I beg to differ with God. You would too, wouldn't you? Okay, folks, you know what? I will admit that he probably has a point. There are limits to these. Really, the line of best fit is limited by how close you really are. If you're way off, guess what? Even your line of best fit won't help you. Okay, this is assuming you're close. He's right. Assuming you're close, the line of best fit is going to help you. So find the inverse slope, and I want to see this calculation actually on the graph. Find your inverse slope. Okay, so it's number divided by number, and that gives you density, and I want to actually see that. I want to see it calculated, because if you got it wrong, it could be that this calculation is closer to the true value than your average. This calculation could give you a better observed value than your average. So, what do I mean by that? That means that over here, this observed value could be this. Oh, I'm sorry. The observed value could be this number, or it could be that number. Whichever one is closest to the true value, use it.
How do you know what's the true value?
I just told you what it was.
It's on the sheet.
Yesterday I gave you the true values. And I told you what yours was. Okay. Any questions? Yes, Sarah. You don't have a question. Any other questions? Yes.
Line of best fit, is there a quicker and easier way to do it than like doing it in the calculator?
No, don't do it in a calculator. Use a ruler.
A ruler?
A ruler. Use a ruler. And I used a piece of paper. So you draw a line that hits as close to all the points as possible. The line that hits as close to all the points as possible. For most of you, a line of best fit is something you've done repeatedly, right? Maybe if you're an agate, maybe you're not quite there, or honest geometry, you're not quite there. Ge- Algebra 2, you do a lot of this, right? Yes? Shh. Oh, okay, I gave Rachel permission to talk. She's the only one. Yes?
I don't remember in there if you said it, but are you just drawing a line from the origin, or are you like
Start in the origin with a ruler and get as close to all the points as possible on that line. I mean, I was using a piece of paper, so it is possible I could have gone closer if I was concentrating. Next. Okay, the rest of the lab should be the same. Data analysis. Tell me what you found out and what problems did you have. Conclusion. This is where it needs to smell a little bit like a cow pasture. You know what I mean? Cows are going to leave behind a lot of what? Yes, leave behind a lot of fat. You got it. All right. So, this is where you really need to get verbose. You can't do this in 2 or 3 sentences. You need to summarize in 2 or 3 sentences how you went about doing this. You need to summarize in 2 or 3 sentences what you found out. And then you need to take a statement, a sentence. That's 7 sentences right there. You need to take a sentence to tell me whether the hypothesis was right or wrong. This should be the biggest part of the lab. For suggestions, make sure that it's a sequel. Don't tell me that you wish to use a digital scale instead of the analog one, okay? Because you're going to lose 5 points right there. Why? What are you doing? What kind of movie are you making if you decide that you want to improve on this way of doing it? Okay, you made a reboot. What do I want? I want change a different variable. Don't change mass, change a different variable. Find a different variable to change. Yes?
So if we were saying that we want like change the material, or is that like facility?
Well, changing the material. No, actually, if you were to see if this would work with a different material. Yeah. Yes, Jimin.
So this title has 2 different questions.
Has 2 different questions. Your hypothesis should have 2 different answers.
Okay, so then
Everything else should be one thing.
okay.
Everything else is one thing. The only thing that's 2 is your title and your hypothesis. Yes? What? See if temperature affects volume. See if, I don't know, see if, well, she came up with, see if you do this with a different material. I mean, think about, come up with the controlled variables, and this time leave length the same, change one of the volumes. Change one of the variables, the controlled variables. That's the easiest way to come up with a different experiment. Yeah, a sequel. Any other questions?